Hello, guys. Today we are talking about our chapter 7. It's going to be about sampling distribution. In slide 5 and 6, we learned what is it about binomial distribution, and in chapter 6, we learned the normal distribution, right? So we're going to extend those distribution and we will mainly focus on sampling distribution. So for preview, first chapter, so we are trying to infer our population using some sample. So the idea is like that. So let's say this is a whole population, or population means all the for example, all the people in the United States. So we want to know, like average wage or an average education, something like that. We want to know that. But the tricky part is what we actually want to know is their actual, wages and education. One way is we can ask all the people in the US. But the problem is there are too many people and it is very costly, So for that reason, what we usually do is, okay, have a very small fraction of people. This is called the sample. So we are trying to have a sample out of a population to guess whatever, things we want to infer. So we are trying to guess our population parameters using some samples. So usually population is unknown, but this is using sample is known, but it's random because if we select this fraction of people, it might give you this number. But if you get this number, it might be different depending on which sample you are choosing. So we're going to talk about some of the properties and why this is important. So as a warm-up question, so let's say X is following normal distribution. We said in previous chapter, N is normal distribution with mean, average, and variance, or sigma square or standard deviation square, right? So which one is random out of this? First thing is X. This is a population. Mean and population variance, and population mean and variance for everything. Can you guess? So I will move to the answer. So only X is random. Why? Because choosing a random chocolate is an experiment. So depending on which one you are choosing, it might be different, right? But mean and variance do not change. For example, I told you earlier, population is unknown, but it's not random. So if it's a given, like let's say population parameter mu and sigma square is given, and it's not random, so it's not going to be changed, so it's not random. So only randomness here is X. So when something is random, we can define the probability distribution because it's some random 30% chance it's gonna come up with something, or 70% chance it's gonna guess another value, something like that. So we're gonna have some kinds of a distribution with some probability assigned to each of the outcomes. So we can, based on that, we can compute the average and variances. So let's say 7 ounce bag hold 210 pieces. So we randomly choose several bags. This kind of thing actually happening in the factory. They said 7 ounce is the proper amount should be in the chocolate, and they randomly usually choose and see some experiments because they cannot inspect all the chocolates in the factory. So they select 100 or even 1,000 or some numbers to get inferences. So from chapter 7, we're going to talk about inferences, and this is a starting point. So let's say X bar is the average weight, per candy in the bag. So do you think the sample mean is random? Yes or no? Okay. Yes, of course. X bar is also random because X bar was based on X, right? Because X bar is a sample mean. Sample mean was based on X. So of course, if as X is random, X bar should be the random as well. So the experiment is choosing 210 pieces. If you had to choose a different bag, sample might be different. So we're gonna talk about some of the properties and mean and variance of this, and then sampling distributions. So sampling is a draw or random sample. Usually N denotes the sample size, and random sample is denoted by this. So for example, in our graph, we said, okay, this is the population, but we are selecting some N number of samples. So based on that, we can get some average and some variances, a variance of wage, similarly a variance of education, something like that. So we are selecting some random sample. Another example can be, if I want to know the average SAT score in UR students, and I instead of asking all the students, I can have 100 random sample and try to get inference close to the mean. So the identical distribution, this is kind of like assumption. Expected value of x1 is equal to expected value of all other values, so 1 through n. So which is mu, and this is equal variance assumption. We're gonna talk about this in more detail later parts. That means, depending on, all the samples are having same variance or and same mean. It doesn't matter which one. For example, whether you are selecting from first sample or last one, it's gonna have the same mean and variance. So our last assumption is independence. So these are actually very important assumptions that we're gonna deal with more later in chapter 11 and 12. In the last chapter, also relevant to your final project. Speaking of final project, I'm planning to give you some instruction sometime in let's say mid-October. So you guys should have about 1 month to work on that, or a little more than 1 month. So this is another example. I will just talk about the project later. Okay, let's say Y be the outcome from a dice. Let's say Y bar is average from n dices. So simply think, okay, let's say we have a 2 sample or 2 dice, 2 dices. So what is the probability that Y bar equals 6? Okay, when do we have, so when we draw a dice twice, and when do we have average value of 6? The only case is possibly the first dice should be 6 and second dice should be 6 as well, right? What is the probability that the first dice gives 6, which is 1/6? Second dice gives 6 with the probability of 1/6. So since it should be happening at the same time, so you're multiplying it. So you can multiply. We learned this from first chapter. Yeah, in the chapter 1 and 2, we talk about statistical independence. We learn, and it was in the midterm, and because we had the independence assumption, so that's why we can just multiply this together. So for example, independence means the probability that Y1 equals 6 intersection, because it should be happening at the same time, Y2 equals 6 is what? Because they are independent, it's going to be probability of Y1 equals 6 times, it should be multiplied because of independence, and probability of Y2 equals 6. So this is a probability of 1/6, and it's a 1/6. So its total should be 1/36. This is how you get. If you are confusing this part, make sure you are going back to your previous chapter, okay? This is definition of independence. That's why we made in previously. Okay. Okay, so there are 36 possible outcomes, right? I mean, the first possible outcome is 1, 1, and 1, 2, 2, 1, 1, 3, 2, 2, 3, 1, etc., etc. So if you count that, it's gonna be basically 36 possible outcome. You know, because the simple math is like, okay, the first outcome, the y1 has 6 outcomes, and y2 has 6 outcomes. So if you multiply, it's gonna be 36 outcomes. So this is how you get the 36 out of these numbers. So we know that expected value of y equal 3.5. That is, so if we are confusing, let me know. This is just 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6, right? Or you can multiply because each of them has a probability of 1 over 6. So as we learned in before midterm, you can multiply 1 times 1 over 6 plus 2 times 1 over 6 plus 3 times 1 over 6, etc. So what is the expected value of y bar? So we know this is expected of y. And how about expected value of y bar? So the answer is, I mean, we can get the word of probability distribution, right? I mean, we learned this in very, very detail in previous chapter, I think in chapter 3. So if we are still confusing this part, make sure you are going back, okay? So we have 11 outcomes, right, for y bar, because the it's from y bar can be 1 if both dices gives 1. It can be up to 6, but we have a total of 11 outcomes. Distribution is symmetric about 3.5. You might want to try the 11 outcome just and then why this is symmetric, okay? Okay, so first finding is like that, okay? So if you do the math, so if you multiply 1 times 1 over 36 plus 1 point times plus times 2 over 36 plus 2 times 3 over 36, etc. I mean, this is how we get the average, right? When you have a probability distribution, right? So we don't just add 1 plus 1.5 plus 2 plus 2.5 and up to 6 and divide by 11. No, that never happened. Especially we have when you have a probability distribution is different. For example, probability that y bar equal 1 is 1 over 36. But on the other hand, the probability that y bar equal 3.5 is 6 over 36. So those are different. So simply, if we just add the whole number, divide by 11 is not fair. So that doesn't work. So you just need to multiply and add that to get the this average. Again, if you are confusing this part, please let me know. Otherwise, you can look at our chapter 3. The first finding is expected value of y equal expected value of y bar, right? Which is 3.5. Oh, well, those are the same. So even an extreme value occurs, it can be canceled out by another one on the other side, because 1 over 6 and 6 over 1 gives y bar equals 3.5. So this same property holds more than these two dices. Second finding is the probability of y bar equal 6, which is 1 over 36. We just went over. That is smaller than this. So I mean, each probability. So this one is actually higher than this one, because for y bar to take extreme value, because this is extreme value, because both numbers should be 6 to get this one average equals 6. So it's called extreme values because it's unlikely happen. So the extreme values have to be repeated. So that's why the probability is much lower. So if y bar is from n dices, y bar equals 6 need to be n outcome to be all 6. So I mean, in previous case, we have 2 dices. So we got 1 over 6 times 1 over 6. But if we have n equal 10, for example, then you should multiply 10 of this, which decreases as sample size increase. For example, if the sample size is 5 and the probability is that small, so it's unlikely to happen, you know. So when you have only one sample size, I mean one dice, then probability distribution is like that. This is y bar, right? But in when you have one dice, y and y bar would be the same because that is only case. So probability is 1/6 and equal across all the distributions. And n equal 5 give you this kind of distribution. It looks like a normal distribution, right? If n equal 10 and these are the distribution. I mean, if you're curious, you might be trying to get some of the numbers. You can do this in Excel as well. So if n equal 25, it looks more like a normal distribution, right? Yeah. So as you can see, as the sample size, one notice thing is that as the sample size increases, what can you see? I mean, this is a variance, right? The variance is actually getting a little bit smaller, right? In general, but I'll just go over this property a little bit later, but just keep in mind. X bar is the sample mean calculated from random sample. And basic properties are some of the important properties. Expected of x bar equal expected value x. This is something we just went over. Another thing is a variance of x bar equal 1/n times variance of n. This is inversely proportional to n. This is something we just went over briefly. So I mean, some notice thing is as sample size increase, how much is spread it out is like a variance or standard deviation, right? So that is inversely related. As sample size increase, the variance is decreasing, right? So that is actually relationship coming from here. Variance of x bar equal 1/n times variance of x. Similarly, if you take a square root of both sides, because a standard deviation is just equals square root of variance of x. So we got the same outcome, inversely proportional to square root of n. So why this is the case? So these are some of the properties. For example, expected, I mean, we already went over some of the examples, right? So let me just go over this really quickly with you, bear with me. So, I mean, this is kind of like important. So what was the x bar? So x bar was what? 1/n x1 plus and plus xn, right? And if we take the expected value of this, so I will just mark as expected lead. So that is like expected value of this, right? So then what? By the property of expected value, you can distribute them out, and you can rewrite this as, okay, 1/n times expected value of x1 plus 1/n times expected value of xn. But what we made the assumption in a couple slides ago was expected value of x1 equal expected value of x2 equal expected value of xn. I mean, So everything is the same, which is mu, right? So we replace that here. It's going to be 1/n mu plus 1/n mu, 1/n mu. But how many mu we have? 1 through n, so it's going to be n mu. In other words, this is 1/n times n mu, which you can cancel out, is equal mu. In other words, this expected value of x bar equal mu. This is how you get this expected value. Okay, so I'm going to erase this. How about variance of x bar? So variance of x bar equal what? So how did we get the variance? By the, I mean, what was the x bar again? So x bar was so let me just start from here. I shouldn't have erased that. Oops. So x bar equal just 1/n, 1/n times n x1 plus xn, right? So like we did before, for expected value, just plug in variance in front here. Variance. So the property of a variance in previous case was this, like variance of ax equal a square variance of x. So we learned this in chapter 4, right? So in other words, variance of 1 over n x equal what? 1 over n squared variance of x, right? So keep in mind, so we can distribute them out. So that would be variance of 1 over n x 1 plus 1 over n x2 1 over n xn, right? So which should be 1 over n squared, variance of x1 plus 1 over n squared and variance of x2 and So we made the assumption previously, right? Variance of x1 equal variance of x2 and equal variance of xn, which equals sigma squared. So if you factor out this using 1 over n, 1 over how many of this sigma square available? There are total of n, right? So we have n times sigma square. But if we factor out this, it's going to be 1 over n square times n times sigma square. So if we cancel out, it's going to be 1 over n times sigma square. Okay. This is how you do that. Okay. Okay. So these are how you get the properties. I mean, I also explained in the detail in the slides, so you guys might want to check it out. This as well. So the larger n, the smaller variability of x bar. This is one of the important property. Variance of x bar equal 1 over n times variance x decrease as n increase. So if n goes to infinity, variance of x bar goes to 0, because I mean this is the properties, right? We said variance of x bar is 1 over n times variance of x, right? So as n goes to infinity, so limit x n goes to infinity, or I mean simply if you don't know the limit, it's 0. In other words, 1 over infinity equal basically 0, right? So in other words, 0 times variance of x would be 0. So this is some mathematical properties. This is actually called law of large numbers. So as the sample size increase, the variance is shrink to 0, so no randomness anymore. So x bar converges to the population mean, so that is called the law of large number. Very important property. So as the sample size goes to infinity, so no randomness anymore, so x bar, which was random before, as we discussed earlier, converge to population mean. That is law of large number. So number of credit cards, let's talk about this. I mean, E of x and variance of x, I mean, you guys should be able to do that, right? We learned this intensively in chapter 3 and 4, and these kinds of questions were in the exam. So make sure you guys take a look at this. I will just reveal the answer, but mean is what? 1 times 0.25, 2 times 0.5, 3 times 0.25, and summate that. This would be some number. Variance, get the mean and take the difference, and then take the square and multiply probability, and finally and add them. This would be your variance. So it's to find that this is the answer. Now suppose that you survey. By the way, if you are still confusing this, please go back to slide 3 for expected value, slide 4 for variance. Okay. If you are still confusing after going over that, let me know. Okay. So suppose that you survey 100 people to calculate x bar. What is the mean and variance of x bar? So expected value of x bar equal what? And variance of this. I mean, you don't have to calculate it again, just using the formula. Expected value of x was, so I mean, previously what we learned is like that. So what we learned was expected value of x bar equal expected value of x. So which was expected value of x was 2. So that's why expected value of x bar is that. So variance of x bar was what? Is 1 over n times variance of x. So previous question, variance of x was 0.5, and how many sample size do you have? 100. So it's 1 over 100 times 0.5. You know, that is your answer. So it would be something using this formula, and this would be your answer. Easy, right? I mean, you just got to plug in the values. So overbooking, if x is 1, if a ticket is canceled and x0 otherwise, and you're basically selling 100 tickets. So probability of cancellation is like that, and what is E of x and variance of x bar? Do you have any idea? So what you note, I mean, you can actually start from scratch, but when x is a binary variable, what was it, average and what was the variance? I mean, you can use the properties, right? Since x bar is, x is a binary variable. So I will just reveal the answer. You know, I mean, expected of x is just p, right? And and then variance is just p times 1 minus p, right? So as a result, expected value of x bar was just, which is equal to this, so just p. And variance of x bar is just variance of x over n, so p times 1 minus p over n. So plug in the number, boom, you get the answer. So I mean, this one we learned in chapter 5. We learned intensively. I explained in detail. So if you forgot about this formula, make sure you are going back slide 5, okay? And listen to my lecture again. So if you want to use the binomial binomial distribution, y is the number of success. So expected value of y is n times p. So the difference here is that x is a binary random variable. Here, y is a number of success. So you should multiply n times p. I mean, this was part of a homework, right? Homework of 5, I think question number 2 or something like that. The cancellation probability was 0.1 and you had a sample size of 11. So the probability that the headset not working and working was 0.95. So you multiply 11 times 0.95. That was time we used this formula again. So again, this is y and the previous was x. So you got to know the difference. And this is how you get the expected value of y and variance of y. And so x bar is equal to the sample proportion. So this is how you get, so basically x bar is equal to the sample proportion of a success. So x bar is y over n. Similarly, you substitute back here, then this is how you get. This one, if you're confusing, you don't have to know, because basically this is exactly the same thing as here, but just wanna explain you, okay, we still get the same answer if we are using y instead. So okay, since most of the time we are more interested in x bar instead of y, so these are some of the properties, but if you understand this, it would be enough. But still, it will give you the same answer. So if x is the weight of M&M candy measured in gram, and it follows normal distribution with a mean equal 1 and sigma or standard deviation equal 0.1. So what is the probability that candy weigh more than 1.1 gram? So you might want to pause this video and try to work on this. This is very important. I might just ask similar question in the second exam, okay? So I'm gonna leave you the answer, but before that, please try, okay? So we are looking for basically probability that x is greater than 1.4. We learn intensively in a normal distribution. If you have no idea of this, make sure you're going back to slide 6, okay? So we are having x. So first thing you need to do is, this is our distribution, and we are looking for candy, which is x. It's random, right? A candy weight is basically a random variable x more than 1.4. That is what you're looking for. So first thing you need to do is find the probability. This is the first thing you need to do, right? And you are standardize it, convert to z-score, right? So basically x, okay, I will just explain just to refresh your memory, that was, so first thing you need to do is find this probability, okay? 1.1, you got to know this one is something you're looking for and you standardize it. So x minus, so we said mean equal 1, right? And variance equal 0.1 is greater than 1.1 minus 1 over 1, right? So I mean 0.1. So we know this is z, so that's why it's a probability of z greater than what this is when you do the calculations 1. So using the table, right? So if we are using the table, it's gonna be always, so since we are looking for, this is 0, and this is G distribution, and this is 1, we are looking for area over here. But whenever you are looking for, looking at the table, the area given in the table is always on the left. So when you look at Z-score table, and this is some kinds of number, if you are going back, this is gonna be about 0.8413. So if we are confusing this, just give me a second. I will try to open those to explain you one more time. Okay, I will just share the screen. Bear with me. Okay, so this was a distribution table we learned before. So we are looking for probability that z less than some number. We said 1, right? 1.00, which is 0.8413, right? This is how you're looking. As you can see, this area is on the left. So graphically speaking, this is how you, this area is 1413, right? 1413. So in other words, if you are looking for this area on the left, right? And how would you do? Just 1 minus 0.8413, right? This is your answer. So make sure in exam and then as well as your homework, you know which one you are looking for, whether you are looking for area on the higher than that or lower than that, but whenever you see the table, it's gonna be area on the left, so you should subtract from 1 to get the final outcome you want, okay? So these were the, how you get that. So basically this is this, so 1 minus this is some number. So let's X be the average weight. And since we know X is normal distribution, and these are something we can get and we were able to get it, right? So we know probability of this is this. So what is the probability the average weight of 4 candies is greater than 1.1? Oh, this is a very important distinction. I was talking about probability that candy is a candy. Just 1 candy, but greater than 1.1, but we are talking about average weight of 4 candy greater than 1.1. This is very important distinction. I cannot emphasize enough how important the difference is. So make sure you guys are working on that. I will explain in detail, but please try to do this yourself and I will reveal the answer, okay? So I'm revealing the answer. You might want to pause the video, okay? So the difference is like that. So you got to find the standard error. So you need to find the standard of so standard deviation. So was what? For example, we know standard deviation previous case was 0.1, but I will just explain on board. So we learned standard deviation of x bar equal what? 1 over square root of n times standard deviation of x, right? This is something we learned in the property. So we learned this in a couple slides ago. So we know this standard deviation here was 1.1, and how many sample size do we have? 4, right? So answer is 1 over square root of 4 times 0.1. That is your standard deviation. So you're looking for probability that x bar is greater than 1.1. In other words, you do the same thing, you know, that would be just subtract mean. So that would be probability of x bar minus what was the mean? 1. And this one would give you 0.05. So you divide this instead of this one. You need to use this one, okay, instead of that one. So because that is something you're looking for. So whenever you're looking for something, you got to know which one you need to use. This is average of 4 candy bars, average weight of 4 candy bars. This was just 1 candy bar. So since question was asking average of 4, so you need to divide by 0.05. and this is greater than 1.1 minus 1 over 0.05. We know this is z, so probability of z greater than, if you do the math, it's going to be 2. So let's go back to our table. Again, this is 1 equal 1 minus probability of z less than 2, right? So this is a very important distinction. So we are looking for z 2, right? So 2, so it should be 0.9772. So it should be 0.9772. So subtract from 1 is some number, very small number, right? This is how you are looking for. Okay, so this is your answer. Easy, right? I mean, if I ask you this on exam, it should be super easy, right? So, okay, so central limit theorem is another very important theorem. So we learned how the mean and variance of X bar behave. We do not know the shape of distribution, right? So central limit theorem, which is one of the most important theorem in statistics, along with the law of large number, states that X bar will be approximately normally distributed when n is sufficiently large. So in other words, it doesn't matter what kinds of distribution you originally have, whether you have a binomial distribution, Poisson distribution, or what kinds of distribution you have, as long as you have enough sample size, and X bar will be approximately normal. I mean, that is very powerful because you don't have to have assumption about distribution as long as you have a lot of sample size, right? So even if when original distribution is not normal, it's okay. Yeah. So it's much stronger than law of large number. Law of large number gives expected value of X bar equal mu and standard deviation of X bar equal this, right? Because that was something we went over previously, right? When we did expected value things, right? So when we have enough sample size, and this was the properties, right? If n is sufficiently large, the central limit theorem gives this, and after standardized, this is what we done. So I mean, something similar to what we have done, right? So you subtract mean and divide by the standard, deviation of X bar, and this would be something. So important distinction is that, so previously it was X minus mu over sigma, but now it's X bar minus mu over sigma over square root of n. So this is important distinction because of this property. Okay, I mean, things we learned from law of large number. And another property was if we have enough sample size of n, then central limit theorem gives this property, okay? Because that means, okay, if we have a sample size large, then X bar will follow a normal distribution with a mean of mu and variance of sigma square over n. We have n here. Previously, it was sigma square, right? I mean, we learned this in a couple slides ago. Variance of X bar equals square root of, sigma square over n, right? So, so we can approximate a binomial distribution by normal distribution if n is large, right? Suppose that you have 400 tickets booked. So suppose you have 400 tickets are booked and the capacity is 372 seats. So a ticket may be canceled with the probability of 10%. So want to calculate the probability that 28 or fewer tickets are canceled. This is actually a practical example you might see when you are working on like a hotel industry or airline industry. They are usually overbooked, because they know there exists some probability that somebody canceled the reservation. So it's not going to be maximizing their profit if they are selling only 372 tickets. They might want to sell a little more because they know out of these people, someone will cancel out, right? So, so let's use binomial distribution to calculate, and let's say y be the number of cancellation. What are the parameters? So we learned this intensively in chapter 5, and also it was part of the first question in homework, and also as well as a midterm. So what are the parameters? So how many sample size we have? 400, right? And these were just capacity, and we have a probability of this. So parameters are always N and P. So the answer is, of course, 410%, because this was the sample size. This is similar to question 5. I mean the homework 5, right? When you have 11 headsets, 11 agencies, so that sample size N equal 400 probability is this. This was the first parameter. So you have a Y is following binomial distribution with 400 sample size N and P. So we want to find the probability that Y is less than or equal to 28. So you can calculate that using Excel or the R program. I mean, I gave you the program, right, for R before. So you can use that. So let me explain you again in our program. Again, I will go to share our program with you. Give me a second. Yep. So we explained this briefly. I mean, in chapter 5, I think. So I'm just same thing. So this is the program. D binom and Y is number of Y's. We explain and NP in the order. This is like, for example, if you are looking for probability of, Y equal 28 with the sample size of 400 and then 0.1. So that is something I will just explain in board. If you want to find the binomial distribution of, because what we want to do is the probability of Y is less than or equal to 28. So technically, this is what? Probability of Y equals 0 plus probability of Y equal 1 and probability of Y equal 28, right? Each of these probability can be calculated using, for example, this one is D by norm 0, which is because Y equals 0, comma, we have 400 sample size, comma, 0.1. This one, for example, is a D by norm 28, because this is 28, comma 400, comma 0.1, right? So summation of this would give you the answer. So 29 of them, but it might be cumbersome, too many codes. So in our program, we have this P by norm. That of 28, comma 400, comma 0.1, that is basically summation of this everything. So this might save you some time, That is basically equal probability of Y is less than or equal to 200 and 28 with N equal to 400 and P equal 0.1. So how easy is it? So just be careful. If you're looking for probability of Y greater than 28, then it should be 1 minus of this, right? So this is another tip. So let's see what you get. For example, this is a comment. So if we do that, this is your answer, right? So 0.023. So 2.35% of chance. So that is the probability, right? Let's see the answer, compare the answer with the slide. Okay. So as you saw, I mean, I used it in slide the Excel file, but you can get same answer using this one. I mean, using our program. So you, okay. So use central limit theorem. We need to transform the random variable to X bar. So remember P equal this and N equal that. So we want to, so that was how you get the answer using binomial distribution based on chapter 5, but this is based on chapter 6 and 7, because we know as the sample size is going to be very large, then using central limit theorem, every distribution can be, X bar can be approximated by normal distribution, right? So we are going to see whether that would work. So expected value of X bar equal what? It's just equal what? So and variance of X bar equal what? So I explained in detail in previous slides, just same slide, but in a couple slides ago, maybe 10 slides ago. So try to do this yourself. It might be on your exam, right? So I will just review the answer, but before that, you might want to pause, okay? So expected value of x equal 0.1, variance of x equal just p times 1 minus p, and standard deviation is square root of variance. So this is what we learned. I explained in detail in chapter 5. So if you're confused, go back, or I also explained in couple slides ago in the same slide. So by law of large number, these are the property. Again, I explained in detail about 20 minutes ago or 30. So by central limit theorem, these are the property. I explained this 10 minutes ago, okay? Go back to the slide. So we know, okay, this is probability that y is less than or equal is probability that x bar is less than or equal 0.07. How do we get this one? Because the proportion of canceled tickets smaller than this one equal this. So these equal this. 28 over 400 equal 0.07. So we are getting x bar as a proportion. So this is property. So you are subtracting x bar minus. So what you need to do after that is as follows. So for example, we know expected value of x bar equal 0.1 and standard deviation equal 0.3 over square root of 400. So if you are looking for a probability of x bar less than or equal 0.07, then use standardize, which is probability of it's going to be x bar minus 0.1 over standard deviation, which is 3 over square root of 400, is less than or equal 0.07 minus 0.1 over 0.3 over square root of 400. So we know this is z, and this would be some number if you plug in the math. It's gonna be actually equal probability of z less than or equal -2. So you can find the probability if you go back those things, then it's gonna be -2, so less than -2, it's gonna be okay. These are the properties. So probability of z, so you need to look at this negative side. Z equal -2, and less than that is 0.0228. In other words, if you draw the graph, this is -2, this area is 0.0228, yeah, or 2.28%. So this is how you are looking at this slide. Okay, so as you can see, these are the answer. How easy it is. So in the binomial distribution, we got this. In central limit theorem using normal distribution, we got this. I mean, binomial distribution using R program would save you a lot of time, but try to imagine if you are doing this by hand or other method, it would take forever. But as you can see, quite similar, right? So that means as the sample size is high, instead of using binomial distribution, you can use by central limit theorem, you can use normal distribution because normal distribution is usually much easier, okay? So the error would be much smaller if n is large. This is error, but it's gonna be shrink to 0 if n is really large. So this is another types of question. So if your insurance company offer insurance for mobile devices, the premium of insurance is like $60. So we calculate the probability of that insurance company make the losses. So these are the probability. I mean, it's like a given, so you don't have to worry about that. Let's say this is some kind of probability distribution in the given, and the company make a loss if the premium, I mean, they are, if X is greater than 6 because the 60 is our premium for the insurance, right? So if X is greater than 60 or they are paying more than what they are getting, then they are making a loss, right? So let's use law of large number and central limit theorem to find the probability that they are making a loss. So, can they calculate the mean and variance using this? Of course, right? You can calculate the mean and variance. we explained, I mean, we went over this, I mean, like a lot of times, you know, 100 times 0.15 plus 200 times 0.1, etc., etc. Variance similarly. So you'd get, you know, expected value of X and variance equal this. So using this, you can get the, I mean, so this is the reason because, you know, I mean, just went over this. We intensively went over this in chapter 4. So this is another thing. First, get the scared of the deviations of X and the mean. So it would be 100 minus 50 square, which is 2,500 times the probability, which is 0.15, 375. Add everything, it would be variance. Okay, so we had the expected value of X and variance of X. So assume 300 contracts. So we are now talking about X bar. So now at this point, you should be able to calculate the expected value of X bar and variance of X bar out of this 300. So with the sample size, how do we do that? So first, please spend at least 5 minutes to try to answer this. This should be very important. I might ask a similar question on the exam, okay? So I will leave you the answer, but by now, given this, you should be able to get expected value of X bar and experience of X bar or standard deviation of X bar to calculate or normalize it or standardize it. For example, these are how you get expected value of X and standard deviation of X bar. We went over this a lot and explained in more detail in previous chapter, and by central limit theorem, this is something you're looking for. So make sure for your exam and understanding, you practice enough to get these ideas, okay? This is very crucial. You get expected value of X bar from expected value of X, and standard deviation of X bar is from here. Okay, and variance of X bar was variance of X over N, okay? So probability of X bar greater than 60 using this. So finally we get this, right? You might want to get this one because probability of Z greater than 2 equal what? This is a probability of basically 1 minus probability that Z less than 2, right? So using the normal distribution table, for example, this one is equal. So it's equal probability of Z less than 1, right? I mean 1 minus probability. We explained this a lot in previous questions. So no, did I say 1? It should be 2, right? So so find that that would be what? Let me just going over this again. So let's go to 2. So that would be here. So 0.9772, 772. In other words, if you subtract that from 1, is that what you are looking for is like that. Okay. So this is how you get that. The risk reduced from 30% to 2.275 because previously the risk was 30%, for example, because if with the 15% probability, you got to pay $100. With the 10% probability, you got to pay 200 and 300. So in other words, summation of this 15, 10, 5, it's 30%. So with a 30% chance, you can make a loss, right? So that was how you get the 30%. But when you have more, with some sample size, you know, some contracts, etc., X bar, on average, you're making the risk reduced from here to here. So I mean, if you guys are taking some finances, this is how the benefit. One of the benefit of basically you want to have so diversifying your products. For example, instead of having one stock, you might want to hold 10 stocks to split out your money. So that is the idea. Let's consider sample size equals 7,500, etc., etc. So what is the probability? Exactly same question, but sample size increased from some number, 300 to 7,500. Please try to do that. I will just leave you the answer. So these are the outcomes. Your probability would be close to 0. So at what this tells you is that, oh, a size of insurance, as increased, the risk will disappear. So that is one of the very important topic in finance, risk pooling. Okay. So this, in rule of thumb, no, there is no mathematical theory requires sample size, but usually the minimum is 30, but as higher sample size, it will be better. What this means is, in central limit theorem, as sample size high, you can approximate something x bar using normal distribution, right? So the minimum required sample size would be usually 30. So as long as you have, sample size higher than this, maybe you can approximate something by normal. Okay. Thank you so much. Talk to you guys later. Bye.